here we are, back for the second in 4 segments of this particular unit. Let's go over where we have been and where we are going to. We have evaluated trig functions for angles other than the quadrant and the special. We used our calculators to do this. You should remember, though, how to calculate the trig functions for angles which are special and are quadrants. I expect you to be able to do those with no calculator. Okay? Now what you can use for these is the unit circle. So that will be allowed on any quizzes and tests. What else do? We use, yes, we just talked about this, we use the graphing calculator to find trig values of any angle. And we worked with the inverse of a trig function, which the inverse of the sine function could be written like this. And what goes in here? The ratio. And what does this equal? It equals some angle. So just the opposite of sine. Well, that's a great S. That's almost as bad. Sine of some angle equals a ratio. So when we talk about inverse here, we're talking about putting a ratio into this function to find out what the angle is. Today, we're going to work on this one, solve right triangles. We'll do a quick review of that in a minute. And then the last two, we will be working through multi-step problems. Well, let's get to it. Now we're going to start, instead of jumping right into it, we're going to start with some errors that are common with using calculator. 1, 2, 3, 4, 5, 6, 7 of these errors, very common. Find the sine of 30 degrees. Well, if we're not using our calculator, it's easy enough, isn't it? But we know sine of theta is the vertical, y over r, the radius, or how else could we say it? Opposite over hypotenuse. So the sine of 30 degrees, we don't need a calculator to know what this is. The sine of 30 degrees is going to be 1 over 2. Or if we write it in decimal form, there it is. So what happened here? Sine of 30, well, that's certainly not positive 0.5. Let's see if we can reproduce that here. I think it will be actually fairly easy for me to do. I'm just going to turn my calculator on, and I'm going to say sine of 30, and I'm going to close parentheses, although I don't need to. Oh, so what is wrong? We know it's, move this over a little bit. We know it's 0.5. I'll show you what's wrong. We're in radian mode. So if we were looking for the sine of 30 radian, we would have the right answer, but we weren't. We're looking for the sine of 30 degrees. So that's very common. You will do it. I may even do it during this course. I should know better, but it's very easy to lose track of which mode you're in. So make sure your angle measure is in degrees if you're looking for degrees. So make sure that these are matching. Second one is about notation. What's tricky about this is that from earlier studies, we're kind of trained to look at that and think of it as an exponent, but it isn't an exponent. This is special notation that tells us that this is the inverse function. It is not an exponent. Okay? It's not an exponent, so don't let that fool you. No way. It actually is an inverse. So when I'm asked to find the cotangent of 30 degrees, if I go to the inverse function, I'll be looking for, this wouldn't be a degree measure anymore, would it? It would be a ratio. How would I actually go about doing this? Since my calculator does not have cotangent on it, what do I do? Well, what I actually do is I first figure out what my tangent of 30 degrees is, and then I take the reciprocal of that. Now, it turns out 30 degrees is one of our special angles that we already know. Cotangent of an angle is x over y. Remember, for tangent and cotangent, we don't even care about the hypotenuse. So in this case, what's that going to be? Our x is the square root of 3 and our y is 1. So it's simply the square root of 3, which is approximately 1.7. Well, this certainly isn't 1.7. Something went terribly wrong here. What we should do, let me pull up the calculator, and we'll turn it on. What we should do is find the tangent of 30 degrees. I know I'm in degree mode. That's good. We'll find what the tangent is of 30 degrees, and then do what? Take the reciprocal. These are not reciprocals. What is the reciprocal key? It's right here. In this, we are looking at an exponent. Context matters. So here we can get the reciprocal, and there's our correct answer. Okay? So be careful. Be very careful. Cotangent is the reciprocal of tangent. It is not the inverse of tangent. Speak TI language. Well, that's only saying you have to be very careful about how you input information into your calculator. Sine squared of 30 degrees actually means sine of 30 degrees squared. And cosine squared 30 degrees really means cosine 30 degrees squared. So when you put it into your calculator, you need to put it in that way. What happened over here is whoever put this in, put in sine, and then they said as part of the angle raised to the second power, and there was nothing for the calculator to raise to the second power yet. So that's why it gave a syntax error. So you don't know the language I speak. So let's be clear about what the language is. It should be done like this. Sine 30 degrees raised to the second power plus cosine 30 degrees raised to the second power. Go ahead and do that right now with your calculator. What does that equal? 1. You're going to learn, have we talked about the Pythagorean identity yet? We'll be talking about that later on. Here's another common error, and it's all about parentheses. What's wrong with this one and what's wrong with this one are both the same thing. The parentheses are done incorrectly. if you want to add 2 to the sine of 30, you want to make sure that you close off your parentheses. Now, if you weren't going to add anything, you could leave it open, you'd still get the right answer. But if you're going to add something to that, you got to make sure that your closing parentheses is there. What happened here? Well, let's take a look at the sine of 60 degrees. We know sine of theta is y over r. And in this case, with 60 degrees, we have, that's one of our famous triangles, or special triangles. We're going to take the opposite, which is the square root of 3, and divide it by 2. That is not the same as what we have here. Again, this was a failure in what we do with parentheses. The closing parentheses should have been around the 3. I'm hoping that by going through these, I can save you a little grief. Parentheses make a big difference. If I'm going to err with parentheses, I err with putting in a pair too many rather than a pair too few. Fifth common error. This is a common response error. That means I'll ask you to figure something out and you will make this mistake in your response. You could give me an exact answer for the sine of 60 degrees. But instead, you go to your calculator. By the way, this is a good estimate for the sine of 60 degrees. What's wrong with this? You should have given me an exact answer. We just looked at, in the previous example, sine of 60 degrees, and we have an exact answer for that. That's the square root of 3 divided by 2. That's the answer we want to be giving. Not an approximation, not a decimal. So keep that in mind. I do expect that you will give me exact answers for any of the special angles. The decimal answer is not an exact answer. Sixth, we only have this one and the next one. A conspicuous input error. This should be conspicuous to you because what do you know about these two ratios? They have very severe limits, don't they? The ratio is going to be greater than or equal to -1 or less than or equal to 1. With an inverse function, what am I putting in here? I'm putting in the ratio. So if I put in an impossible ratio, this is impossible, can't be greater than 1, then the calculator is going to immediately say, no good, and it'll give you a hint, there's something wrong with your domain, something wrong with your input, and we know what it is. Since the numerator of cosine, right here, this is the ratio, remember, we're working with the inverse function, it's going to equal an angle. The numerator, the adjacent, right here, otherwise known as x, is never going to be greater than the hypotenuse. The hypotenuse is always the longest side in a right triangle. Since it can never be greater, the fraction here, this ratio, can never be greater than 1. So this is clearly impossible. Finally, another common error. And this is involved in calculating the inverse of trig functions when you're working with the reciprocal ratios, the reciprocal partners. Remember, just as our trip to the hospital from the traffic circle in Portsmouth, when we did the inverse, we went in reverse order and we did the opposite operation. What would be the last operation? Let's look at it this way. If we were going the other way and we had cotangent oh, that's not a good example, sorry. If we were looking for, let's see, the cotangent of, what was the one we just had a few minutes ago? Didn't we have one? Right there. The cotangent of 30 degrees. We use that one. Do you remember what we did? This will be a little review for us. We look at the triangles. Oh, it's good to be drawing a picture. So the triangle for this, I'll draw it right here. Make it little. 30 degrees. And what's that triangle look like? 1, 2 on the hypotenuse. This has to be the square root of 3. And cotangent is x over y, or square root of 3, 1.7. To do that on our calculator, how did we start? We took the reciprocal relationship first. A reciprocal of 1.7, or the reciprocal of cotangent of 30 degrees, was the tangent of 30 degrees. So when we're working with the inverse, the very first thing we're going to do is take the reciprocal. So we'll say the arctan that will give us the correct answer. To find, and this is true for any of these inverse functions that are associated with the reciprocal ratios, take the reciprocal of the ratio, which in this case is tangent, and calculate the angle. Okay, those are the common errors that you might see. Now we're going to move on to the big news of the day, solving triangles. Just a little review of how we name things, so we'll all be using the same vocabulary. The 3 vertices of a triangle are named with a capital letter. This is a point A, point B, point C. Or we could refer to the vertex as angle A, angle B, angle C. Associated with that are the angle measures, alpha for angle A, beta for the measure of angle B, and gamma for the measure of angle C. There is a clear relationship between the vertex or the angle and the name of the opposite side. You always name the opposite side with the small case version of the angle. So capital C, point C, becomes small c for the length. Just a little thing to watch out for, the contingency, or congruency, notation that you learned in geometry. We don't follow it here. So again, context makes all the difference. These two angles are clearly not congruent. All this little line means when we're talking in trig is we're talking about an angle. If we were studying geometry, we would never put those in as looking as if they were congruent. Solving triangles. Here, if you know any two measures, you can solve the triangle. You know, any two measures, you can solve the triangle. Now, right here we're looking, remember what our whole unit is about. We're looking at right triangles. That's important. With right triangles, we start off knowing one of the angles, don't we? With we know that that is 90 degrees. Now, one thing I should point out right now, if there's no indication of the units that are going to be used for measuring the angles, you can use degrees or radians. We think of this as 90 degrees, but we also could say it's pi over 2. And these are both radian measures, aren't they? And there is nothing wrong with 1.57 except that it's really not exact, whereas the pi measurement is exact. I prefer you, if you can give an exact answer, to do so. So if you end up with something like this, let me pull this over. Okay, turn this on. 1.57 divided by, I want to pull pi out of there, factoring pi out. See, it isn't exact. It should have been 0.5 because this is 1/2 of pi. So it is a little dangerous if you are supposed to be giving an exact answer to use radian all by itself. Now sometimes the problem does call for radian, not pi radians, but just plain radian. Oh, I should go over this, the knowledge of geometry that you're going to be using. You know that the sum of measures of the angles in a triangle equal 180 degrees. That's going to be important. You also know that in a right triangle, 90 of that 180 is right here, leaving the acute angles to add up to 90. So the acute angles are complementary. Alpha plus beta equals 90. The other welcome knowledge you have here is the Pythagorean theorem. Now, for this one we're doing right here, we know A, where is it? Right here, opposite angle A. So side A is equal to 33. Side C, which is the hypotenuse, is equal to 65. I can already figure out what B is, can't I? I'm going to take, and let me write it out for you. It's going to be C squared, hypotenuse squared, equals A squared plus B squared. Now I want to know what B squared well, I actually want to know what b is, but I'm going to find b squared first, and that's going to look like this. B squared equals c squared, and I'm going to subtract a squared from both sides. So now let's pull up that calculator and do those calculations. C squared, I'm going to do 65 squared plus, forget that, minus a squared. Gee, that would give us the wrong answer. Okay, 33 squared. So now I have 3136, and I want to take the square root of that in order to know what b is equal to. It equals the square root of b squared. So I'm going to raise that to the 1/2 power, right? That's how you can take a square root. Remember that? So my answer is 56. So I'm able to get, if I have both sides, I'm able to get my third side without ever even thinking about trigonometry. But it's not quite so easy to figure out what these angles are. I am going to have to use trig for that. I'm going to have to use one of the ratios, but I always stick with the straightforward ones, sine, cosine, or tangent. If I want to figure out what alpha is, and I know my y and I know my r, which ratio should I use? The one that has the hypotenuse and the opposite. Which ratio is that? That's sine. Now here's a case where I actually have the ratio and I want to know the angle. So a more direct way for me to do this would be to say, okay, I'm going to use the inverse function. I'm going to put in 33 divided by 65, and that will give me my angle measure. Do you remember what my calculator was set to? Yeah, that's right, it was set to angles. Yeah, it was set to angles, set to degrees. So second function, sine, and I'm going to put in the ratio 33 divided by 65, and my answer is going to come out in degrees. So there it is, 30.5, 30.51. So for alpha, 30.51. Now I don't have to use any more trig because acute angles are complementary. Therefore, what's complementary to this? Ooh, a little less than 60 degrees, right? 59.49. And I am wrong to not put the degree sign on there. If the degree sign isn't there, whoever's reading your work will think you're talking about radians, which we are not. Here are some examples right out of your workbook, and you should go ahead and do these. We won't solve them completely here. You can finish them up in class, but we'll do a little work with them here. I advise you to always draw your triangle. Doesn't have to be to scale. You'll notice I'm pretty bad at it. I've got this one now. My C is 14, that's opposite gamma. My B, I don't know what the length of B is. This would be B. I don't know what my beta is. Alpha I do know, 21 degrees. So I have this measure and this measure in addition to knowing that I have a right angle. So what do you think I should go for first? Well, if we've got two of the three angles, we certainly can figure out what this one is, right? 21 from 90, 69 degrees. All right. And then we're going to have to use a trig ratio to figure out what, oh, I should mark it. We don't know what A is. To find out what A and what B are, I can use sine of 21 degrees equals A over 14. Or, another way I could write it, I can re-express it. A equals 14 times whatever the sine of 21 degrees is. Let's pull it up and find out. Turn it on. The sine of 21 degrees is equal to 0.35837. You could just write these first four. I'm going to want to multiply that times 14 to figure out what A is. 5.02, I guess when we round it. So 5.02. At this point, I could use the Pythagorean theorem, couldn't I? Or I could go with the sine of 69 degrees equals B over 14. Now where am I getting that? Let me show you my thinking here. So here the angle I'm focusing on is right here. And what's opposite that is B. So opposite goes right here, and the hypotenuse is always the radius, so that goes there. So I could figure it out. Example 10. You're going to figure this entirely. You can do it now or back in class. If I'm given an angle and a leg, so I know it's a right triangle, I've got one angle. Let me draw this. It's a right triangle. I've got this angle, which is 77.2. Oh. That's right, give me a chance to draw it again and maybe better. 77.2 degrees is my alpha. I don't know what my beta is. The length of A is 29.5. Make sure you do these drawings. It will help you. Now I can figure out what beta is easy enough, can't I? Because I know that these two have to add up to 90 degrees. So what would that be? 12.8 degrees. I always have to check my simple arithmetic. That's where I usually go wrong. No, it's okay. So now I can do, just as I did over here, I can say, all right, the sine of 77.2 degrees is equal to A, which is 29.5, over C, and I can solve for C. I'll figure out what this is. Of course, I'll have to find an equivalent here. What would C be equal to? Divided by whatever that is. We know it's going to be something less than 1. So you go ahead and do that one. And then if you're given an angle and a leg, so again, we've got that it's a right triangle. And we've got alpha, that's given to us. And we've got, boy, it looks just like the one we just did, doesn't it? What's the difference? Well, the only difference really is the way the angle is expressed. This is expressed in DMS. So you should express beta in terms of DMS as well. What would that be? Well, to get this to 60 seconds, you would add 16 seconds, right? 16 seconds. And to get this to 60 minutes, you would add this one and how many more? 47 more. Is that right? Is my arithmetic okay? And then to get to 90 degrees, when you've got 38 here and another one sitting over here, so 51. So I think if we add these up, we get to 90 degrees, but that should be checked because I'm notoriously bad with arithmetic. It's funny. I love mathematics, but the arithmetic, yuck. Okay. So now how would you figure this out? Well, you can actually put that into your calculator. Let's try it on. I know I'm in degree mode. Sine of 38. Oh, excuse me. I don't know why it does that. Sine of 38 degrees, and where am I going to find degrees? Right there. And 12 minutes, which I also am going to find the second function on apps, and it's right there, number 2. And then I need seconds, which I cannot find in apps. I can find it only use, oops. Oh, I cleared the whole thing. All right, very good. That gives me a chance to demonstrate it again. 12 minutes. It's funny, I thought I could just clear out the last thing I'd written, but no, I can't. And 44 seconds. 44, and here I'm going to use alpha. I was so anxious to use alpha, I was skipping right by. So you can put it in like that, and you will get a ratio. So let me pull that aside. So when we write this out, let's say we want to know what C is. Say the sine of alpha equals A, which we know, 102.35 over C. So C is going to equal 102.35 divided by the sine of this angle, which we have right here. So I want to divide 102.35 by this number. How can I do it on my calculator quickly? I can move this from the numerator here into the denominator so that it can be dividing. And I find it's 165.46. 165, whoops, wrong one. 165.46. 6. There are so many little ways to screw something up. There. Okay. Let's look at what this example is. A leg and a hypotenuse. I don't think this is all that much more difficult, is it? Let's see. This looks like one of the first ones we did. Angle and oh, maybe not. Okay, this case we don't know either of the angles. We haven't actually seen that before, have we? We've always known one of the angles. So in this case, we don't know either one of those angles. We do know this is a right angle. We know A is 8 and C is 13. So the obvious one for us to go for is alpha. Use sine for alpha. Sine of alpha is 8 over 13. However, when we know the ratio and we want to find the angle, we're going to use arcsine. And that's going to tell us what the angle is. My calculator remains in degree mode, so I can just turn it on, not have to worry about that. And I'm going to second function sine 8 divided by 13, that's the sine ratio, equals almost 38 degrees. 38.98 we'll say. 38.98 degrees. Now I could figure this one out easy enough, right? I just subtract that from 90. What about this? Can I figure B without having to use trigonometry? You bet your life I can use Pythagorean theorem. You go ahead and do that. This last one is a little trickier because I've given, or Stu Schwartz has given this to you in 2 different units of length measure, plus the request is that you express your answer in this format, degrees, minutes, seconds. So make sure you do that. This is either going to all be converted to inches and say A is 24 inches, or the other thing you could do is convert it all to feet and say B is 1.25 feet. So you choose one or the other and then work with it. Make sure your units are the same. And when after you figure out what this is as a decimal degree, you remember how to convert it. You're going to find that in the second function angle. Well, I think this has been pretty good. We'll finish up those exercises and then go on to your homework when you get into class. I look forward to seeing you.